Good afternoon, and I welcome you all to the next session for this Hadoop installation. Sir had already given the fundamentals of Hadoop, and I had already presented what are the prerequisites and how to set up Hadoop installation. From so let me start where I had earlier stopped. We had stopped on this thing. What we had done is we had moved the Hadoop extracted folder from the initial Hadoop account to the OPT folder. Now what we will do, we will change the mode of this. We're going to change the mode of Hadoop. That will be done by this command sudo chmod 777 Hadoop 2. Hadoop, the current version. This will change the mode of this 777 means read, write, and execute. After that, what we will do, we will edit the bash rc file. We will just go to the newly created Hadoop account. We will go to the HADACC account. Now we will use sudo nano, or you can use gedit, although nano is quite better. Bash rc. We'll paste some lines inside this. We'll paste some lines. This is the file what we are going to paste. We are going to configure the various variables here. So right now, as I earlier pointed out, this Java is located at this location slash user lib JVM, and this is the current version we are using. I will just copy all of these things and put it inside this bash rc file. Copy, and for pasting, use Control Shift and V at the end. Then press Control X, then use Y, and that means this has been already updated. Now to check what is the current location of this Java, we will use this command echo Hadoop home, echo $Hadoop home. Let it print the location where is this is located. Okay, see, this is within the /opt folder. That's fine. Now we are going to update other files: mapred, Hadoop env.sh, various configuration files, sdfs site.xml. We'll just go to this current location of the Hadoop, that is in the /opt file. This Hadoop account, we will go inside the Hadoop. Then we see that inside this etc and Hadoop, we see various files. There are various files: yarn.site.xml, mapreduce, sdfs site.xml, like this, core site.xml, and this sdfs env.sh. We have to configure all of these files. Use same command sudo nano or sudo gedit to configure the various files. Let us configure env.sh file. So for configuring this file, what we will do, we will just open first of it. These are the set of files which we need to update. sdfs site.xml. Use one of the sudo nano env.sh. This will open. What we will do, we will comment the Java home here, because this is not the actual location, because we have already updated this location in the bash rc file. So for that, what we do, We will put the actual version and we will give it the actual location. If you do not do this thing, that means you will get serious errors there. Put below it Control Shift and V, or you can directly paste it. Then use Control X. Then use Control X and Control V to this thing. Okay, that it has been updated. Now use other files like sdfs site.xml, core site.xml. We will open this file. We will update it accordingly. Inside the configuration tab, you have to paste all of these things inside the configuration tab. Copy it. This has been pasted. Okay, this is updated. Now all other files, hdfs site.xml, put all of the lines inside this configuration tab. These are the configuration parameters. Now remember this thing. I have I have created an I have created HADACC account for Hadoop, but right now the file is this is meant for SD user. I am writing SD user, so be careful what you write. If you create an this this configuration is meant for creating an SD user account, but I have created a HADACC. Eventually when you will run the SDFS name node format, it will give some errors, so remember that. It's going to give some errors. At last you can see. So make sure what you write, you must know what you are writing. Use always, whenever you create an account for Hadoop, use SD user, because by default they have given the locations like that as SD user. But here now I have just created the Hadoop account, that is HADACC. That means this file has already been updated. Now, okay, this is also SDFS is being edited by the root. We have to use yes, and that means it's fine. That means this has been updated. Finally, what we will do, we will use, okay, that's fine. This is sudo nano sdfs site.xml, yarn site.xml, because this is for map reduce. You will propose various configuration parameters here of yarn. This that means we now need to create map reduce site.xml file, because if we look in this etc Hadoop folder, there is no map reduce site.xml. There is just a template, but this template has all of the operations that are required, all of the means fields that are required in map reduce site.xml. So we are going to copy it. We'll use copy command, sudo cp map reduce site.xml, a template to mapreduce site.xml. We'll create this file mapreduce site.xml. Will it is XML. It's not a template. Okay. That means if you use ls, you can get the new file. See, this new file is already created. It will have all the contents. Now we have to update this mapreduce site.xml file. See here what we have. The MapReduce framework name is this is the name, and its value is yarn. That means it will use all of the yarn processes. MapReduce has a limitation. That's why we use yarn. although working is quite similar. It processes the data in the same way. So that is updated. That means all of this has been done. Now what we will do, we have to create directories for it, because we have already configured various parameters in hdfs site.xml. We have to configure various parameters there. We have to make temporary directories. See, I had not created HAD user. I have created HAD It is going to give an this thing error when I will the use some commands for during the later installation. Hadoop.temp, it creates various directories inside that temp. SDFS, data node and name node. We have to create these two directories. Same location, but the name will be data node. We have to change the owner of these things. It's quite simple, although it's a little bit it has many iterative steps, but it's quite simple. If you know what you are doing, it's quite simple. We will change the owner of this data node. See, the change of owner, I have used Hadoop account because HADACC is the actual this user for accessing Hadoop. But in that set configuration file, I had not updated it. It's going to throw error. So be very careful with these things. That means this has been done. So finally, what we have to do, we will use various this thing. Start dfs.sh. Start this thing, that is done. All of that is done. That means we have to just use start Hadoop name node format SDFS. We will type this. I've cleared the screen. We will use this Hadoop name node format. It will take some time. See, this got formatted. Start dfs.sh. It will start the name node on the local host. That means this has okay. This is completed. Now just a minute. Installation. Second part. Open with is now see. That means I have already formatted all of these things. This is the final part. How to view the output in the browser. Start dfs.sh is meant for this, starting the dfs in your node. It will start name node, data node. Starting name node, data node, because dfs has linked with only these two things, name node and data node, and besides the secondary name node. Now we will use start-yarn.sh, which will run all the current processes. GPS, if I run, let me see what sort of process will come. See, see, various processes have come up: name node, secondary name node, and data node. That means DFS is working properly. And besides that, what we have: node manager, and resource manager. That means all of the processes are working fine. Now what we can view the output. How to view the output? These are the, you have to paste some things inside your browser: http, that localhost 5070, and that other one link which I had earlier shown in the presentation. This is how you set up Hadoop in a single node. See, all of these processes must come. JPS stands for Java processes, secondary name node, data node, and name node. These are meant for DFS. Resource manager and node manager, these are meant for yarn. Now what it will show: the location of this thing. You have to open link in new tab. You can get, okay, the local host information. This will give the name node information. See, let me wait. This is the output. This is your cluster resources. Now within cluster resources, no apps have been yet been submitted. Nothing has been pending or completed. So nothing has been used. So besides that, there is only one. Since we have set up node in a single cluster, there are only one active nodes. No nodes are decommissioned. No are healthy nodes. No are unhealthy nodes. That means no are lost nodes. No are unhealthy nodes. This is your information in the this thing. By using yarn, this is the output. This gives the cluster resource. All sorts of things are there: what schedules are running, what are running, everything it will give you. It will give what sort of cores are there, what is the status of this thing. Now this is fine. Now other thing is that how to get the DFS information, distributed file system information. See, okay, just wait a minute. Total memory is 8 GB. See, you can get all of the cluster resources. This is the resource manager. This you call it as resource manager. See, virtual cores used, maximum allocation for every core. 1024 memory is allocated by default. Otherwise, you can change also. It's a configurable parameter. Now this is the resource manager. How to know the information about the file system? You can.
Meet, just a minute. I'll interrupt you.
Yes,
You
sir.
do one thing. I will just come in at this point of time. Just I'll 15-20 minutes. I'll brief on the next session. Then you can continue from here. You keep it
Okay.
ready. Okay.
Okay.
So I mean, this resource manager, actually what Mir is telling right now. So actually that is I mean, currently whatever versions we use, that is called, we call the yarn resource manager. So that actually that is Hadoop 2.0. Okay, so it stands for yet another
Another resource negotiator.
resource
Yes.
negotiator.
Yes, sir. There were actually there were some limitations which I earlier pointed out in MapReduce. So based on that, they propose another idea, what is called yarn. It works
Yeah,
in
yeah.
the same processes, same set of things. It works, but it has some that limitations of the MapReduce were overcome here in yarn.
Yeah. So I will just I will take over. So I will show you the next step, how it operates and also, and Mir can carry on with the demonstrations. Okay, very briefly. So I'll just present my screen, Mir.
Yes, sir.
Yeah.
I have stopped, sir.
Okay. So be there maybe 15-20 minutes. That's it. Then you can
Yes, sir.
continue. I think participants had expressed their desire to the coordinator that they want to see more of hands-on.
Yes, sir.
So okay. So already now, at least with the demonstration now, all of you must be aware about bit of the terminologies are, all of you must be already convenient with it. So when a client requests, okay, any user requests for any operation, maybe a reading of a file, storing of a file, writing to a file. So I mean, this slide shows the sequence of operations. I will not go into details. I mean, everything cannot be shown in demo, but This is just the sequence of things. Okay, so there is a client protocol through which first of all the client has to request the name node about what operation it wants to do and which file and all. So in turn, as we already discussed, that name node will have a the entire metadata. So from there it will do a table lookup and find out the exact locations of those the exact data nodes. Okay, so those all those conversion and all are taken care of by the control mechanism already present in the name node, and then the name node communicates with the data nodes through a data node protocol. Once that is there, a request response based communication over socket is established between the client and the data nodes. Okay, so that happens. Then in case the name node goes down, so there is also a name node protocol through which the secondary name node is also updated about all the updations and all transactions and all whatever are maintained in the name node. So everything is a replica copy is made. Just a minute. Just give me a moment. Just a moment. I'll just come back. Let me take the class. Yeah. Okay. Sorry for the interruption. Okay, yeah. So this is how it goes forward. So we'll just see the sequence of operations which happens for a read operation. Just very briefly go to it. Okay, so maybe this slide would be better because this shows that if required, I'll come back. There is also a write operation, right? Yeah, write operation. We'll not go focus on the read and write, but how the basic operations happen. This slide is the best one. So let me go there. So initially, the client has an application which is installed. Once you install the Hadoop, it comes. So from there, a request is sent to the data node because the sorry, excuse me, to the name node. So the name node, because it has all these metadata, so it does based on, usually it's the request for a file because it's a file system. So name node has all the data, all the tables corresponding to it, like a file having how many blocks at which locations. So it responds back, the name node responds back to the client application with this the data node number and the block location within that particular data node. So once the client application gets this information, so then it directly contacts, suppose let us assume that it has told that data node 4, okay, data node number is not given, this is the, out of all these data nodes, this particular data node has to be written. Okay, so it depends on the operation, of course. So let us assume that this is a write operation. So the client application, once it gets the data node and the location within the data node, so it it contacts the data node. Okay, so this shows this is data node 3. This is a scenario, just a demonstrative scenario, which shows that it has two racks, rack 1 and rack 2. Rack 1 has data node 1, rack 2 has, it has 3 data nodes, 1, 2, 3, and rack 2 has 2 data nodes, 4 and 5. Okay, so now once that because the block position location within the data node is also known, so directly the client application contacts there, makes a writes the data. So before writing the data, of course, something has to happen. So the operation has to be opened, the file has to be opened. So file is opened, the file is written, and then finally, as Mir has already shown, so we can also configure it, the number of replications. So it can be 3, 5, whatever the user wants, and based on the how they configure the Hadoop while installing. So based on that, n number of replications will be made. So those once the data is copied to the first copy is made, then the replication copies are also made. Usually replicas are kept in such a way, so they are it's a triple modular redundancy is used. Okay, this is the general this thing where 3 copies of the 3 replica copies of each block is made. Some of them are kept at the same data node. Some blocks are of course kept at some other data node within the same rack, and some of course at some other rack, because in case that is the reason why we do what do you call that, replication, because in case this rack goes down, so this rack will, if it goes down, it will go down with all the data nodes. So some replication has also have to happen at some other disk, at some other rack also. Okay, so once that operation is completed, so then the that acknowledgement is sent back. Okay, block write completed. So that is sent back to the client application, and the client application finally closes the operation. Okay, in between something also happens, which we did not mention very specifically. I mean, this already we discussed, but what we did not discuss is the heartbeat messages. So there should be some mechanism. So name node might get stale at some point in time. Stale means, I mean, as we already discussed, that commodity hardware is basically, I mean, that was a motivation of designing Hadoop altogether right at the beginning. So that is why name node might go down. Sorry, the any of the data nodes can go down. So when the name node has all its metadata, once at that point in time, if a rack goes down or some data nodes within a particular rack goes down, then it might create a problem, because in that case, the I mean, data node which has gone down, how does the name node know that? So if the name node doesn't know that, then a new client application requesting for a block can be forwarded to a node which actually is not alive in that sense. Okay, so that the name node gets to know by I mean, a sequence of heartbeat messages, for which the timing is also fixed. It can again be configured, but exactly I don't recall. If me recalls, he can some point in time he can mention it. Okay, so heartbeat messages are like the pulses which the name node keeps track of in order to confirm whether a node is still alive or not. This is shown only for this particular rack, but this is true for all across all racks. Okay, so in this way, write operations are done. Again, the read operations are done similar. So I'm not going into further details, that you can see what we will discuss now. I mean, not going to so much of details. If time permits, Mir can explain this. I think he'll also show you in demonstration the HDFS, these different daemons. Okay, what I have not discussed till now is the computation part of it. So till now, whatever discussions I have done is mostly focused on the HDFS part, the Hadoop distributed file system, how it keeps replication, how, and Mir has already shown how these configurations can be done, the installation process and all, which he will again continue after this session. I mean, after my portion. Okay, so now MapReduce, I'm sure most of you know it. If you don't know, it's just a very, very brief overview, but this will lead us to a point where we will just tell to you that based on this idea, what I mean, how we carried forward our research and what contributions we made in terms of performance optimization. Okay, should be interesting to you. So as we already, I'm skipping a few files because I mean, it's better to have more emphasis on the hands-on demonstrations. Okay, so even these slides, if you are aware of it, you already understand. If you have no idea, then it's very difficult to understand from all those slides. So better I come to one particular slide. Okay, so the fundamental principle of MapReduce is it's a computation which basically the computation it what do you call that? It leverages on this key value pair formation. Okay, so basically it depends on parallelization of IO operations. Why IO operations? The computations will be done in the computation servers, in the processors which are there in the server. But then this is a secondary memory, right? We are talking of the file system, which is there. I mean, HDFS has to be there in your secondary memory. So anyway, this processor to hard disk, I mean, secondary memory communications, all of us know these are very, very slow. So the only way to improve performance of such operations is by parallelizing them. So it depends on parallel IO operations basically. So MapReduce exploits this particular area. It attacks that area, how it can parallelize a number of IO operations. Okay, so this shows there are, I mean, the key, I mean, the way it is done is by forming from the, I mean, see, the computation will be done, but the data required for that computation is available in the hard disk. I mean, in the HDFS storage. Okay, so, and the storage is done in terms of a number of blocks, as we already discussed, and the information of all those blocks, which block is located in which location, at which rack, all that information are there with the name node, right? So now the MapReduce programming paradigm is a different way of conceiving the programming paradigm. Usually when we write a program, for example, C program, usually, so we do it with the idea that all the instructions will run on the processor, and any data which the program would require, that has to be brought from the disk. Okay, so that part here is not there. It's, as we already discussed, there is no one disk. It's a collection of many number of disks across different racks and across different clusters also. Okay, so to improve the performance, what we do, we, based on the problem, so this is problem specific. So based on the problem, we try to convert that particular problem into a problem with key and value. So here it shows the example of word count process. Okay, a word count program. Okay, so how that is processed, so how the key and values are uh, separated out. So a word count means if you give a file, the input is a file with a number of words. Okay, so alphanumeric numbers are there. So the goal of this program is to, it's a standard benchmark program. There are other benchmark programs also which Mir will demonstrate and he'll explain. Okay, so this example is very intuitive. So what emphasis, please don't forget the goal why we are discussing it. This is very easy to understand in terms of how for this particular word count process we are converting it into a key value pair. Okay, so let us assume that the total input is these are the total set of words. Okay, it can be anything, just for demonstration purpose. So simple thing. So here we see that there are 1, 2, 3, 9, a total of 9 words. Now, as I already discussed, the MapReduce operation leverages its, draws its power from the power of parallelizing IO operations, and the disks are this file is stored in the file system in the disk, so it's an IO operation. So how do we make this computing parallel? So what is done is that the first phase, usually it's the name suggests, map and reduce. So this map is the main phase and reduce is the main phase. So in case of map, what is done, as the name suggests, so the computation is split up, and different portions, the same overall computation. So here we had to in fact actually count total 9 words. Okay, and then what is the final result? We say that after, once this file is read, we come out with this output, that this word bear appears 2 times, this word car appears 3 times within this set of 9. Okay, so 2 2 2 6 plus 3, 6 plus 3, 9. So this 9. So this is the input, this is the output. If that is clear, what we are doing is that we are mapping this into like into different splits, input splits. Okay, so instead of reading the entire data, so we form splits. Okay, so how to form splits and all these are, there are a lot of details there, so that we can see later on in the demo session also. Okay, so it's a very intuitive example. So every line has been shown as a single split. So it can be how to split them. Later on we'll discuss, when we discuss what type of work we have done, research work we have done. We'll see that we have tried to different optimization strategies, like how to place these different splits in the map phase at specific locations, specific racks. So before, while a file is being written, that time only related correlations can be found, and then that can be done. It will of course induce a lot of overhead, but then the once those files are read, that time we'll get some performance benefits. Okay, and we can also do some amount of shuffling, some amount of innovation in the reduce phase also. So this also, I think, Mir, please try to at least show at least the approach you explained. Okay, so what type of, this is a very new, very few people have done work, so we are also have done some good work here. So that will be demonstrated. So once these splits are done, this map program actually now it counts. So within this split, how many numbers are there? So this formation is a key value pair. So here the key is a word and the value is the number of occurrences for that particular word. Okay, so now this again, there are, for different problems, this splitting phase and shuffling phase, and sometimes also called combiner phase. So many sub steps can be done. Okay, here it's a very intuitive small example. So you could have directly given it to one reducer instead of reducing it with so many reduced stages. It was possible that we kept one reducer, and then that one reducer would be fed with all these different mapped intermediate outputs. Okay, so here it finds a keyword deer, and then it sees checks across this how many deers are there. So it finds that here it is there. So accordingly, it concludes that deer this particular keyword occurs twice. So similarly, it would have done it for all the from this split to this split to this split, and then finally concluded. But then think of realistic scenario, big data scenario, where even if you consider the word count program itself, so then there can be thousands of a file can be as something like a 1,000-page book. So 1,000-page book will have thousands of different words, unique words, and some common words like the, and is. So these words will appear many times. Okay, so think about it. So if all of them will has to be reduced using a single reducer, this actually creates a bottleneck for the uh, reducer itself, because ultimately the connection of any one of these all things happen through buses only. So if the bus traffic through the it uses a there is a limitation on the bandwidth of any link. Okay, so if thousands of splits and millions of splits keep on wanting to write to the same reducer, there is a maximum capacity at which the reducer can actually receive all those splits. Okay, so it leads to queues and waits, sometimes loss at the reduce stage. So that is why we reduce. Usually it's a way like we keep a number of reducers. Okay, so these, how many reducers to keep, how many map phases, how many splits to make, these are dependent questions, problem specific questions. Okay, so I hope that is clear. Combiner, so anyway, combiner and shuffle, these phases are not compulsory. It's up to us, and here we can also put a lot of innovation. Okay, this type of work. Similarly, there are other benchmarks also. So I request him, so show some of the other benchmarks that you have used in your work. Okay, Hadoop scheduling is a very basic thing, so I will not cover. How in a MapReduce scenario, how when the jobs come, how does so this is very intuitive. If you knowledge, if you know about Linux scheduling, which I assume that everybody knows. Okay, so you can come in now and start the Hadoop benchmarking part. If time permits, I'll come back and see how we can intelligently place data within the Hadoop cluster. Okay, so that is before actually data is stored. Whenever a file comes, so how many splits to make, all this, how many splits to make, and where to locate all those, which rack to allocate for different blocks, how many blocks should be there for that file. These are different important questions which can be which is a configurable thing, and the name node does it. But before doing that, it is also possible. So Hadoop doesn't place any policy before like this, so that it can co-locate the data with the computation. However, if we have some amount of data, suppose a few GBs of files we have, let us say we have a file corresponding to the weather of a city. Okay, a particular city. So weather for the last 30 years, or maybe the weather of different cities as different. All everything stored as a single file, like in an Excel file, and there are different tabs within that Excel file, and different weather columns corresponding to them. The data are all kept in different tabs for different cities. Now it's a single file. So how to break them into different blocks? Hadoop usually doesn't take care of, doesn't account for all this different information. It simply splits it up into blocks and just stores them randomly, absolutely randomly. Okay, so the rack numbers are, and it just, while keeping them in random, it just makes sure that some off rack nodes are also used. Okay, so if if the replication degree is 3, 2 of the blocks, so the same block will be replicated 3 times, and 2 of the blocks will be in the same rack somewhere, and the third block has to be there at some other rack because of the availability requirement, as we already discussed, right? So this as we discussed, the Hadoop is open source. This Apache Hadoop version is open source, so we can program it, and before in the name node, we can, instead of making this policy completely random, it is possible that we can put some logic as to which file, which blocks to be located at which locations. How do we do that? It's a very intuitive thing. So suppose if you are suppose at any future point in time, I want to know the weather, I want to do some analysis with the weather of let us say Shillong, my city. So in that case, so if Shillong city's data, which is maybe of a few, let us say 600 GB, 600 GB 2 months, let us say zero point 0.6 GB, okay, over a period of last 30 years, 0.6 GB. When we break them down into 64 KB blocks, so there will be a few thousand blocks, okay, few tens of thousands of blocks. So those tens of thousands of blocks, now where to place them? So now you see, when we do an analysis for Shillong city, it is quite in common sense that we will be requiring reading the data for the same city, right? So in that file, what we discussed in that file, whether for Shillong, whether for Delhi, whether for Kolkata, whether for Chennai, whether for 50 different cities are there. Shillong is one of them. So here we can put some logic as to while placing the blocks itself in an intelligent way. So that is what we did in one of our works, intelligent data placement, how to place them so that the goal remains the same. If we can somehow or the other ensure that data and computations are co-located, so if the different co-locate data, so which data? The related blocks. So our goal is to find out the related blocks. So there can be different mechanisms to do this. So you can try to do it mathematically by seeing the previous history. Okay, so let us see. I mean, it is possible to keep a watch on this data as to which blocks are requested by which programs, and then based on that, we can of course try to find out a pattern. Okay, so like what do you call that? Correlation. Okay, so we try to. It is possible. This is one particular way which we did. We can try to find out some relationships, some correlations among different blocks. So in that way, we can form certain blocks in a particular clusters and certain other blocks in some other clusters. Okay, just like very simple logic. Okay, so as I gave you the example, so if you have data for 30 years, so we would rather prefer to keep all the 30 years data in the same rack. Of course, there is a replication. So at least one in a replication, in a triple modular replication, TMR, triple modular replication, the default policy in Hadoop, at least one block definitely will be there in some other rack. But here we can, that logic we can implement. That is up to us. Okay, so instead of using Hadoop's native way, the inbuilt way of placing the data, we can put some intelligence, which later on we'll see this can be done at data placement level, and I'm sure Mir will also explain to you about something further. I think this he can explain. So Mir, you can continue if required. I can again come back and continue from here. Let us continue the demo. Yeah, please go ahead.
Sir, thank you, sir.
Any questions, any queries at this point in time? No, okay. So Mir, you please take over. Huh?
Yes, sir. Okay, sir.
Please continue with the demonstration.
Yes, sir. Okay, when previously we started, okay, all of the, let's see how to obtain the output. Remember that these all sorts of this ports we have already given in the configuration. That means whatever you do in the configuration, you can always see what has happened. There are two links, one in which we can see all of the applications running. That means node manager or the resource manager. Another one is the name node information. This will show all of the resources which are in the cluster right now. Right now there is only a memory of 8 GB total, and only one virtual core is there. This will give all the information. Total allocation is 4 cores. Quad core. This is a quad core system. For this is 1 GB. For every core, virtual core, we give 1 GB of memory. It's a configurable parameter. You can change it. Various sorts of scheduler are there. You can check it. Everything you can check it after you successfully install this Hadoop schedule. It will just tell you various things. And this is your name node information. Name node information gives the information about your whole of the file system. That means not it's not a simple file system, it's a distributed file system. You cannot view the this distributed file system via the terminal or like that. It's not a normal file system, it's just an abstraction. It's just an abstraction. You cannot view it. You can view only within this thing. Various things are there, you can check it out. See, configured capacity. What is the total capacity of this DFS? How much DFS has been used? What is the non DFS used? DFS remaining. It will give all the information. Which nodes are missing replicas, live nodes, dead nodes. You can check everything here. What is the checkpoint time? Checkpoint time is the last information. Means that at because sir already pointed out there are heartbeats going in between. So based on that heartbeat, you will say that okay, at the last checkpoint time, this was our status. This will tell you the like this thing. This data node usage. What is the minimum, median, maximum, and standard deviation among this thing? Right now there is not there's nothing in the SDFS. Name node and C. Storage, what is the storage directory? We already created the directory. Home, inside that Hadoop account is the this account used for Hadoop. Inside that we created a temp directory. Inside that SDFS we created name node and data node. See everything. This is the storage location. You cannot get it by this thing by command. You can only view it here. It's I already pointed out. It's just an abstraction. It's not a normal file system utility. You can browse the file. Right now there is nothing. No data available because nothing has been there. This will give the block size, everything, replication. This is all about installation. See, now you can stop the various services which are running. These are all sorts of services are running. You will first of all stop all these services. Stop dfs.sh. That means this name node is going to go down. Name node and data node. Always follow this procedure. You should not cancel it directly. You should always use such commands. Otherwise, there might be some serious errors. That means DFS only takes care of these three things: name node, data node, and secondary data node, secondary name node. Stop yarn.sh dot sh is dot sh. Yarn resource manager, node manager. This will automatically get stopped. Stopping node manager. See GPS. Nothing is there apart from Java. That means all of the things have been successfully this thing. This will not be accessed. This will not get accessed because it's already stopped. As I said, it's already stopped. And just verify it, it won't run again. So this marks the end of this Hadoop installations. Let me wait for a little. Are there any questions? Are there any questions for this Hadoop installation? Hello? Hello? Are there any questions? Are there any queries in this Hadoop installation? Yes, yes, Mr. Vishal, yes. You can go on. You can switch on your microphone. Yes, Mr. Vishal, you can put your question. Cluster ID is cluster ID is given by default. I do not know much about whether you can change the cluster ID. It won't serve whether if you change any cluster ID, it won't serve any purpose.
Okay.
We have to work for performance optimization. We do not have to do matlab, various things. Although you can Google it whether you can change it or not. I have not done anything
Okay.
like that, changing the cluster
Okay.
ID.
Thanks. Thank you, sir.
Mr. Vishal, is there any questions, please?
No, sir. I have asked that question that what are the hardware requirements for that? Any specific hardware we need to install it?
No, 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 no. See. Hadoop, as sir has already pointed out, Hadoop as is this question is asked by Mr. Vishal.
Yes, sir.
Yes, sir. See, there are no specific hardware requirements. Hadoop can be installed in any system. That means commodity system, means cheap systems. It does not require servers. That means you can set up Hadoop with your laptop. Although laptops might come with good configuration, also with some low configuration. It it can run with any system. You install any Linux system here. Suppose you install Ubuntu. Ubuntu requires quite a low storage. Then you can install this Hadoop. It does not require some special hardware for it.
Okay, sir. It is a open source, sir?
Yes. Hadoop is open source. You can view the code. You can view the code. You can read the code.
Okay, sir.
Anything else?
Okay, sir. Thanks from my side.
Thank you. Thank you for asking question. Any other participant having any query with the sir's presentation or with my demonstration of installation? Hello. Is everything fine? I think everything is fine. Can I start again? Okay, let me start. If there are any questions, I can come in between. Okay, the now let us since Hadoop is already installed, so the main question is how to get to know whether your cluster is performing good or bad. By good or bad, I mean whether the performance is fine or not. Means your IO is performing better, your network is performing better, or your CPU utilization is performing better. So for that requirement, we require various sets of benchmarks to be run on cluster which measures various performance parameters of the Hadoop. Now, as I earlier pointed out, why benchmarks are used. First, benchmark is I think it went twice. Benchmark is used to know about the performance bottlenecks. Now, when you set up your cluster of suppose we have set up in a single node cluster. Now, if we since it is a distributed system, we have hundreds of nodes. So all nodes do not perform equally or they do not perform well. So to know that which nodes perform well, which nodes perform better, or what are the bottlenecks in our distributed system. So we run various benchmarks. So basically, benchmark is run to know about the performance bottlenecks. Now, what happens when we put various loads into the distributed file system? We get to know, okay, what are the issues in the cluster. After you put various loads, you run various sort of programs inside your clusters to know various bottlenecks. Besides benchmark the big data gives a complete visibility of the performance as per the required classification. Also, what benchmark classifies, it classifies the various statistics of the program, like as the completion time of the job or the running time of the job, performance. That means how is the network, how network is performing, because in a distributed system you use various resources. You use the CPU resources, you use the network resources, you use the IO. That means it measures the whole parameters of the this thing of your network. That means throughput on the cluster. If you give 100 jobs, okay, how 100 jobs are performing. So sir earlier pointed out like that schedulers. Now if we sir had just means given an idea regarding that FIFO scheduler. FIFO means first in first output. That means when there's a job queue in a distributed system, there's a job queue. When you put one job, the cluster, what it does, it runs the first job. All other impeding jobs, all other jobs which are inside the stack, they will not be addressed until the first job is completed. That means it's a problem. That means if a first program is quite big, there will be a huge response time for other jobs because they have not yet started. So for that, what we have used, there are various schedulers. So by default, it's FIFO. There is also called fierce scheduling. I think this fierce scheduling scheduler was proposed by Facebook. What it does is every job is given a fair sequence of, means it's given fair time. By fair time means if there are, suppose job one comes, it's job one, it has, suppose it has 10 tasks, 8 tasks got executed. Now there are two now another job comes, it has also few, suppose 5 tasks, so three tasks can be launched in the cluster. That means this gives a good performance as compared to FIFO. So there are various things. So based on that, we study benchmarks. Now in a Hadoop, there are various benchmarks. Now the most common benchmark what we have, that is the word count benchmark. That is the word count benchmark. What the word count benchmark is about? What the word count benchmark is about? Just a minute. Let me go to the this one. Escape. Getting hand. I do not know. Let me show it. Sir has already sir has already discussed about this. Like this is the, is it visible? Is it visible to all?
Yes, it is visible.
Yes, yes. Word count process. What does word count process means? Word count process counts the occurrence of words in a text file. You have a text file. A text file is composed of various words. So what it does, it counts the occurrence of various words. The words are called keys, and how many times the this thing, how many times this keyword comes, that means the value pair. Got my point? Now suppose the input is, although the input here is quite small, input is like this thing: deer, beer, river, car, river, deer, car, beer. This is, means this is a very simple, means simple programmed simple way to know how MapReduce program works. Now what it does, since it's a distributed file system, it will create, we do not process a single file we do not process file as a whole. What we process, we create various splits. It's like that. MapReduce is a divide and conquer strategy. That means a big problem is divided into a number of small problems. That means consider this input as a, consider this input as a very big input, means a very big file. suppose of hundreds of GB, suppose of this text file we have. So what we will do, we will create input splits. That means we divide this problem. because we are not running program on a single cluster, we are not running program on a single node, we are running the program on a multiple nodes, because it's a distributed system. So we will create three splits here. Suppose deer, beer, river, car, river, deer, car, beer. Fine. Now, after the splitting is done, this done by Hadoop by default. You do not have to do anything. Everything is done by Hadoop. Now, what it does, map process starts. That's what map is, one of the important phases of map reduce. So, map process start. What map process starts? It it takes the input split and it checks the occurrence of word. Within this split, deer is occurred once, beer is occurred once, river is occurred once. Within second split, these map tasks are running on various different nodes. Remember, it's a distributed system. All these are done parallelly. Parallel. Imagine a very big text file. Various map runs, they are running on various different nodes. Now, car, river, car will be counted once, car will be, again, there's a car, it will be counted once, river will be counted once. Fine. Now, in the third input split, deer, car, and beer. What happens is deer will be count once, car will be count once, beer will be count once. Now, since these map tasks are done parallel at various nodes, now what we do, we will shuffle this data, because this is an intermediate output. See, mapping is just an intermediate output. So together, what is the total condition? We will shuffle this data across any node. Suppose what it will shuffle, sort and shuffle, what it will, beer will be counted twice. Beer from, suppose beer from this node and beer from this node. Car will be counted thrice, like this and this. Deer will be counted twice, like this thing. River will be counted twice. Now what it does, shuffle. After shuffling and sorting, what we will reduce it. That means beer is twice, car is thrice, deer is twice, river is twice. Is it fine? Finally, final result will be obtained. Final result is like this. This is the beer is twice, car is thrice, deer is twice, river is thrice. Then the whole strategy is divide and conquer. Here we divide, here in the map splitting part we divide, and here we merge. That means divide and conquer. If a file, normally if you run such a program in your single system, suppose it takes an hour to count the occurrence of words. You write any C program or you write any Java program for that. But with Hadoop, since you do parallel computations, that means the job will be finished quite early. That means this is the whole sequence of this word count processes. This is a word count. This is one of the benchmarks, one of the simplest benchmarks in Hadoop. Are there any questions for this thing? Hello? Hello? Hello?
No, sir. It's okay.
Okay. Is that okay? Let us run this word count benchmark. Let us see. Since Hadoop is already installed, let us run Hadoop benchmark. Is that fine? Let us run that word count benchmark. Is that fine? Let me show how to run it. See. Let me go to the news section. Okay, here is the download section. Okay, this is the word count benchmark. Now see what happens. Hadoop is already installed into the system. Hadoop is already installed into the system. I will look for the JPS. JPS shows all of the processes are running. As pointed out earlier, data node, this name node, and secondary name node are meant for DFS. Means when you run start-dfs.sh, these three daemons will be invoked. When you start-yarn.sh, resource manager and node manager should be invoked. Otherwise, that means there is a problem. Now these are the all set of things, all set of daemons which might be there when you run JPS. Okay, this is the working directory. It's not doing much. Let us see. So we will create a file. Let me create a text file. Sudo nano wc stands for word count hyphen text. You can create any file name. It's not a big deal. Let me write something inside this. I have saved it file. Use ls to verify okay this has been created or not. That means this file is there wc hyphen text. Now see. Now see, remember one thing. One important point is there. Can anybody tell me whether is this file in the local file system or it is in the DFS, in the distributed file system? Hello? Is this file in the local file system or is this file in the distributed file system? Can anybody tell me, answer me that? See, when you create this sudo nano wc hyphen text, this file is not in the distributed file system. This file is always in the local file system. By ls, you can get it. Okay, within this Hadoop ACC, within this home slash Hadoop ACC, you are having various things. Examples.desktop, Hadoop version, Hadoop this extracted file, Hadoop extracted file, Hadoop tar file, Hadoop TMP folder, and WC text. This all is in the local file system. That means which you can access from the command line. Now we for generating the output, what we have to do, we have to put this file, this word count file, this file which has a set of words in it, we have to move it to the distributed file system. Let us see how to put it. Remember these commands. SDFS DFS hyphen put home dot Hadoop account wc text. C SDFS DFS stands for okay, we are putting, okay, now we are invoking SDFS. You got my point? Now we are invoking SDFS for that. SDFS DFS. Put means we are putting some file inside the DFS. See, see, let me tell the SDFS DFS invokes okay, we are putting some file inside this DFS. Now to put the file into the DFS, we need the location of the file. Now the file in the local file system is located in the home Hadoop ACC slash WC text, and we are putting the file slash by default means root. We are putting it into the DFS. That means this this slash home till this WC text. This is your local file system, and now this will be the location inside the this DFS. You can, this says okay, this file will be placed into the DFS. Now see what happens. Let us see -ls slash, see what does it give. See see this file is already placed in. Now after this command, hdfs command you have invoked, what happens, this file will be placed inside this DFS. Who is the user accessing it? It is the HATACC. Because during installation, what we have, I said create a username for user account for this Hadoop. I had created this user account for Hadoop, HADACC. Now this will be the time when you have uploaded it into your file system. This is your actual file, /wc text. See. Now how to view the contents of file? Let us see that also. Same cat command, but what you have to do, you have to always, these same commands will operate. You have to use sdfs dfs. Then that means the system must know, okay, we are not accessing a normal file system, where it's basically an abstraction. So for that we use sdfs dfs. Otherwise you cannot get, you can never get such a file. See, this was the earlier text file. Cat command prints what is inside the file. This inside wc text file, this I have printed. This is my name, I work in Hadoop, like this thing, various. Hadoop has a number of benchmarks. Now that means these are the set of commands for accessing and for putting file, or for getting the contents of the file inside the SDFs. That means, let us see how this, there are various jar files. Okay, let let the command be there. I will explain it line by line. Now there are various jar files there inside the Hadoop. These jar files, they include a list of programs, list of benchmarks which you can run. See, now if we if you means if you have gone through that Hadoop installation process, I had earlier moved the Hadoop to the /opt location. Within this location you can get all the set of jar files. This /opt Hadoop 2.10.0 share Hadoop map reduce examples. This will give set of map reduce examples, various map reduce examples which Apache itself gives. Where invoke this thing, see what happens. And one more thing, remember that you have to, this thing will not run in your, this thing will not run in your normal, if you access your system in a normal way, means normal account, this will never happen. You cannot get it, because this is meant for, this account is meant only for Hadoop. So see what happens. Word count means I am invoking the word count benchmark. Input, for input, it's not input, it's the actual file name. WC text is the file which we put inside the HDFS, and you have to write output. See, connecting to resource manager. This is the location. This will take some time. This will take some time. See, this will take some time unless it gets started. Submitting tokens for the job. This is your job ID. You can get this information also via that resource manager. Running job. See, this is the running job, and this will, to track this, you can use this thing. This, see this, you can track it down. It takes some time for the job. Resources, see, the various resources are there. Memory is there, virtual core is there, various things there. When you set up, you will get to know a lot more than that. Now if we say, see, both of things operated. Now, as this is a map reduce program, both map as well as reduce has started. This will go on until the program is completed. Okay, map is, see, map has been completed. Map is 100%. Then finally reduce will come into action. Reduce will take some little time. See, that means this job has been successful. See, map is 100%, reduce is 100%. That means since this was a very little, means only a few words were there. That means uh, this program got uh, completed very quickly, very fastly. So what else it does is it gives the job ID which is successfully completed. Now, l- if we look at these various things, these are various set of counters. Counters means, that means it gives various sets of information, for how long the job took to complete, when it was submitted, when it when the map got run, how many map tasks were executed, how many slow nodes were there, various information. See, map reduce framework, map input records were 5, output records were 29, map output bytes 277, various things, input splits bytes were 94, various things, failed shuffles. Because since in a distributed system you cannot get guarantee when information from one node to the another node can might be passed, it's not always sure that it will get passed. So if it does not get passed, so based on that, this failed shuffles will come here. Various things will, CPU time spent is various things, physical memory, virtual memory, everything information, some errors if there are, file file format counters. See, various things, bytes read and bytes written. See this, that means this completes our job. This completes file system counters, number of bytes read, job counters. See, this is a little job, only within a minute and a half it got completed. Besides, see, this is the most important part, job counters. Number of launched map tasks. Normally, the map task is 64 MB or 128 MB. Since the text file was not so long, so only there is a one map task. And there is only a single reduced task. This is a configurable parameter. You can launch as many as reduced tasks, but by default, it has only launched one. Data local map task means those tasks in which the data is present itself in the node. Sometimes it's not possible that data is present into the node. So for that, what it does is it has to use network for bringing data from other data nodes to this data nodes, because by default Hadoop has a default replication factor of 3 in a multi-node cluster. So it might not possible to give to have data local tasks. So when that is not possible, it has to take data from other nodes. So that means this is only a local map task, because this is only a single node. So the
Acha,
total.
1 minute, just Mir. I will just come in now. Just
Yes,
let us see if there are any queries, because you have to anyway at in 5 minutes you have to stop. So if there are any queries, something, or else you can keep, and you can put your questions in the chat box also, so that we can start with those questions next session. Okay.
okay.
You please conclude in 5 6 minutes, huh? And then
Yes,
you let us break, and
sir.
Moya, please stop the recording in 5 minutes. Huh?
Yes,
I will
I'm
also
done.
go for lunch and I'll come back on time.
I'm done.
Okay, sir.
I'm done, sir. The data local map task, I said that it's not always possible to guarantee data is always present on in a node, since it's a single node cluster. So there is a data local map task. Otherwise you can get all of the information. What's the total time spent by all of these things, whether in reduce or whether in map task. I think that finished this Hadoop benchmark. Are there any queries for that? If there are any queries, you can let me know. See, within this DFS, you can check what sort of you can see the output. You can see various things. Let me go inside this DFS folder. You can view it in the command line. You can view it in this thing, also in the browser also. See, this is the output. This is the output of this program. That means this part hyphen r hyphen this 50, this is the output file. This is the output generated by the word count program. Now if you count, this has been these are the set of this thing, key value ps in for this text file. For the input file, this is the output. You can view either in this thing in the command line. You can view it inside this DFS that in the browser also. So this see browser file system, you can check it. There will be a part R this file. See output, this one is the success and part R00. See Hadoop, this is the contents. You have viewed in this you have viewed it in the command line, you have viewed it in this thing localhost also. This concludes the word count benchmark. Are there any queries?
Sir, here it is using single processor.
Yes,
How data is divided on multiple nodes in this example?
I'm not getting your question. What?
Actually, we say that it multiple nodes will work. The data will be processed parallelly on multiple nodes.
Yes,
But
yes,
here we are using the single processor, so it is now only single processor is working to process it. Then how
yes, yes.
multiple processing is done here?
See what happens since we are configuring Hadoop on a single node. So it will work on the set of processors my system has. When you configure in a cluster will have many nodes. They in each node there will be multiple processors, some four, some two, some three, some four, like that. So based on that it will work. That is up to the Hadoop. That is not up to you. That is
Okay.
up to the Hadoop. Since I am configuring it in a single node, my node has my system has four cores, so it is going to work in a, at maximum it is going to work in a four core, or there are virtual cores. They divide the core means processor into two. It's based
Sir,
on Hadoop. It's not
I
what
just
you
want to inquire that how will it store the unstructured data?
what unstructured data.
How it will store it? What
Unstructured
will
data,
be?
see,
Yes.
as sir has already pointed out, Hadoop has an ecosystem. For if there is an SQL type data na, suppose
Yes.
some rows columns like that, so for that we use there is a special thing. There is a special what we call it as for storing this relational database. It's called scoob sqoob, for storing unstructured data, mostly, which is not SQL based data. So for that we use HBase.
Okay.
That is a part of ecosystem. Right now we are not focused on that thing. Okay, what are the various sets of, okay, how XML data is stored, how this various other things are stored. So but the data is stored in a distributed file system.
Okay.
That is the thing. Any more queries?
Okay. Thank you, sir, from my side.
Okay, okay, thank you for asking question, sir. Any more queries? Are there any more queries? Moya, hello Moya, sir.
Yes,
Yes, I think
we can end the session.
yes, yes, we can end this session. So, yes,
Okay, we will be back at 2:30 p.m.
2:30 p.m. Okay, that's then fine, then fine. You can stop the recording. Thank you, thank you, thank you for being
Okay.
with us. Thank you.